Hey, so welcome to our next lecture in neural networks and deep learning. The plan for today is that we will finish what we started last time about transfer learning. Most things we have covered there. We'll just do now two more ways of improving the type of transfer that we have. This should only give you somehow an initial idea of what is possible. There is a lot of work on how to improve the transfer from hidden representations from one task to another. And we learned some, or the most common or most important ones already last time. We'll have a bit more look on that. And that should give you hopefully a very good starting point. Then the second part of today is that we then start with a lecture on self-supervised learning. And this we will see is very strongly connected to transfer learning, because one could claim that the most typical way of doing the first step in transfer learning, so to learn the initial model, is by now to train these models in a self-supervised way. And therefore, this is really essential. We'll see that the big advantage is that we can use huge amounts of data in order to learn then exactly these types of representations that we will then be using in the second step. And this is, the most common thing, I guess you all have heard about this is how it's used in large language models. But before we are coming, let's finish the work that we have done on transfer learning. And there, the challenge we were addressing is what is referred to as catastrophic forgetting. That means that in the fine-tuning step, somehow the dangerous thing is that we overfit to the fine-tuning data and we forget what we've learned before. And therefore, of course, don't have the large benefits anymore. One way to do that was this replay. Another successful idea is to do that, to address that by the loss function. So how that can be done is we of course have in the transfer step, in the second step, in the adaptation, we're using our loss function to update our parameters. So we try to minimize our parameters given the data we have, and then calculating the loss between the neural network output and the reference label that we are having. And one trick we already learned is that it's very easy with neural networks to add additional losses. So this is the default one. That is our main goal that we want to have. We want to be very good in predicting our training data. However, it sometimes might be good to have additional constraints which we can put in as their additional loss. And in this case, the idea is, oh, maybe it's good that we'll still be somehow a bit good on the old data still. How can we achieve that? We're saying, oh, we want to change as minimal as possible, so that we're not just finding the best model that is performing on the new data, and using the old data as only as a starting point, but we're saying with a side constraint to make minimal changes or as few changes as possible. How can we do that? We try to limit our changes. And this time we're saying, or we can do that by looking at the difference between our initial model and the current model. The model is mainly represented through its weights. So the weights are also just like a large vector of all the possible weights, and then we can do the difference. And a good a good estimate at least, or a decent estimate of how different two models are, is that we're calculating the difference between the weights. If the weights are all very similar, hopefully the model is also somehow similar, and then we can say that this is a good estimate. So we are estimating the similarity between our initial model and the model that we are currently having, by the difference between the weights here. And then this is our additional loss, which is added here. So if we're adding things, we're preferring solutions where this difference is as small as possible. Because that means that, yeah, we are hopefully having a decent, good initial model. Now, of course, this is not like, super perfect, this measure, because maybe some parameters are more important for the output. All this is not considered, but it's a decent, approximation of that. And therefore, I mean, as it is a decent approximation, but there's two ways of like why it's important that some parameters are more important. On the one hand, of course, then the distance might be not so well calculated. On the other hand, it might be also idea that, yeah, maybe it's better to change parameters which are not so important. So maybe we should prefer to change parameters that are not that important and do not change parameters which are really essential for our initial model, because then we might destroy the idea. And that is the extension to that, which is referred to as the elastic weight consolidation. You see the difference in the loss function is not really huge. The only difference is that we have here an additional factor which says how important this feature is in our initial model. So if a feature here, or if a weight is very important for our initial model, we are saying then you really should not change that. On the other hand, if the F value is low and this feature doesn't have a large influence on the final model, then yeah, it's fine to change that, and we can learn additional things. So it's a bit, I mean, typically these large models are heavily over-parameterized, so you can also get a decent performance with a lot less parameters. And the idea is, can we somehow find out which parameters are not so important for our current model, and then store the new information in these new parameters so that we don't override the knowledge that we have stored in the parameters, which are super important. Now, of course, there is the big questions: how do we calculate our FI? So how can we estimate whether a model is important or whether a feature is important for our model or not? And the idea here is that you can do, if you're interpreting the model in a Bayesian way, so that you have a probability distribution over all parameters, then you can estimate these by the Fisher information matrix. And then that means you once have to calculate this matrix on your initial data, and you have to store it with your initial model. So the FI is also fixed. And then during training, you keep that. The idea is that you look for each parameter on how fast does the probability of the correct solution decrease in this dimension. And if it's very fast decreasing, then you shouldn't change it, because you very fast get a bad model. While for models where it's not increasing fast, you can change these parameters. You could also visualize that a bit. So this is your initial task A, and you have found the best model here, which is theta A. And you have a bit a space here, which says here you have a relatively low error rate or low error of this model. So all in the grayscale gives you decent, good models for your model. If you're now trying, then we know the yellow one are good parameters for your second task. And that now means if you're doing no penalty, you're just training, then your model will gradually go into like the best performance on this model. If you're just doing the L2 norm, you still go in this direction, but you limit yourself, so you might end somewhere here. And the idea is now with the elastic weight consolidation, you try to stay in this area and then look how you can get the best performance on the second task without leaving the good performance task in here. Of course, there's quite some additional math behind it, but I think the important thing is first at least to get a bit the intuition. So the idea is really that there might be there's not only like one good solution, but there's like several decent good models, and you want to go somewhere where you still have a decent good models for both of your tasks. How does that perform? Here is some numbers. So you see in blue first on the left one over the training time. So you first train on task 1, then you train on task B, and then you train on task C. And if you do that here, you see that you're always going down in performance on task A, because here is the optimal for task A, then you're losing, and then you're further losing. On task B, you're getting better here, and then you're losing again. And on task C, you're the best. If you now do elastic weight decay, you see that you're not really losing that much on task A. You're also not really losing on task B, and on task C, you're maybe not equally good, but still very good. So the idea is really that you don't lose too much on your initial task because you don't want to forget them. Here it's for more tasks. You see, the more tasks you have, the faster you're dropping your performance, and here you're still staying quite high. Also, we had these numbers already last week, so where we talked about catastrophic forgetting. So if you just train your model on the new task, you forget really the performance on the old tasks. If you do elastic weight decay, you see here you're not getting as good, so 30% instead of 70%, but you're staying significantly better there. And then, of course, it can be combined with what we had before. For example, this is the weight factorization, and the best performance somehow is achieved here when you combine weight factorization with elastic weight decay, so that you have the ability to learn some new models, which you then only apply in the new case. And for the general models, you try to keep them as similar as they are. Any more questions to this type of approach? Good. Then, one last idea at least, and that is what is referred to as meta-learning, where you really try to scale up the things. So the question is, you have a lot of tasks which are quite related, and the idea is now, this is now for the first step, how can you learn a good initial model so that it's then very easy to learn a new model? So you have your meta training data, which consists of a task consisting of training data here and test data. And again, training data and test data. And then you have your testing data, which is again has some small amount of test data, train data to learn the new task. And then you have your test data. So the task here is really, we don't want to learn a model in the first step, which is good at a single task, but we want to learn a model where it's then easy to learn a new tasks, and that you can evaluate in this scenario. That's why it's often also referred to something like learning to learn. So the task is not you learn really a specific task, but how you learn a good initial setup so that you can then fast learn new things. There is a general framework, and especially for neural networks, it's mainly meaning then that you try to learn a new task with your initial model. So you want to have a fine-tunable initial model. So again, the idea is, what is a good initial model so that you can fast learn new tasks. The nice thing is now we'll also again do the basic formulas that all these types of the fine-tuning itself is completely differentiable. That means that you can do that as your objective, so that you're saying, oh, it's a good weight update step if afterwards I can fast train the new model, which is this model agnostic meta-learning. So some idea about that. So in this case, our optimization problem, what we want to optimize, is a bit different. So we don't want to have, like now for one sample, that the prediction is very similar, but our initial parameters should be in a way that the loss of the final model compared then calculated on the task-specific test data is minimal, so that you have a good starting point to learn then your final model. And your final model here is built by a function based on your initial parameter and the training data. So you take your initial parameters, then you have a model which depends on your training data of the test training data, which gives you then the task-specific model. And then you look how good is this task-specific model on its test data. So that is a loss function. So the question is, how do we train this? So how do we perform the theta E? How are you normally doing that? If you have initial parameters, how do you get the final model on your example test case? What did we do all the time? How do we get from initial model to the task-specific model? Yes?
We do gradient descent.
We do, yeah, so the fine-tuning, so which is exactly the gradient descent. So what we get is we get from our to our task-specific model by taking our initial model, doing then one or several steps of gradient descent, and that is our final model. And that can be expressed again in a formula, and that means that we then do our updates here of our initial model by looking, if we are going in one direction, how easy can we then go to the task-specific models? So how low is then the gradient to do the fine-tuning step? So you look if what update to my initial model is good, so that if I then would do 1, 2, or 3 steps of fine-tuning, I'm very good at the other ones. So again, graphically, what step do I have to do on my initial model to go to this point, which is near to the optimal models of all the other models? And that is what you try to do in meta-learning or model-agnostic meta-learning, that you try to find this point where it's easy to go to all the task-specific models. And then you can do by just then in each gradient step, do then several gradient steps to the task-specific model and check whether this is good. And again, here, the nice thing is you don't have to typically do, you see the big advantage of like having automatic calculation of the gradients, because then you just have to do the forward pass and don't have to think about how to do all the gradients, but that will be done automatically for you. Good. So what you hopefully keep in mind from the lecture from today and from last week is what exactly is transfer learning, that you have this idea of transferring some type of knowledge to another. And this is really like one of the main advantages of neural networks, that you have this type of general architecture where you learn some type of hidden representation, which is hopefully a good representation for your task, and then you are of the knowledge in there, and then it's easy to solve the other task. So you learn a general representation of the input data so that you can do easily these types of tests. And that enables the transfer learning. We see we can freeze, of course, we can slightly adapt, but it's really important that you have learned these types of hidden representations so that they are not only useful for what you're currently doing, but also for other things. And you don't have to relearn everything all the time. If you think about an image, if in your hidden representation they're somehow encoded, oh, here are 5 animals and so on, this is already a very dense, good representation, and you can then do very easy more tests. If you think of words, if you have a representation which somehow not, of course, readable for a human easily, but it's encoded there that this is a verb, or this is a noun, this is a city, this is a person. If these information are in there and you have learned them in your different layers, then these information help you to faster learn new things. If you once then have learned how to extract that it's a named entity, it can recognize names, although on your named entity training data, you might have never seen this type of named entity. The most standard or most efficient way of doing it is fine-tuning, which is quite easy because we just continue training. So you just switch the task, and now you're not training on the initial task, but you're training on some other task. And then the challenge is there that while doing that, you might have this type of catastrophic forgetting that you're forgetting what you have learned before. And in order to prevent that, there's different ways. One thing which is currently very often used is types of adapters, where you try to change some stuff only and do not allow to change everything. By only allowing to have small changes to the model, of course, you're preventing the model from forgetting everything, but keeping the most important and general knowledge in there. Good. Any more questions to transfer learning? Yeah, I hope that means things are halfway clear. And then we can continue with the very related lecture on self-supervised learning. And here we are again, we'll have look at this type of transfer learning. That is why it's so related. The main thing is that last time we didn't really focus on the first step of the training. Only in the very end, we had this type of meta learning where we try to learn a representation which is easy to transfer. The self-supervised way is now looking at it at a different way. It's saying, oh, maybe are there other ways to get to our initial model? What do we need about our initial model, and how can we get a good initial task? Because, I mean, sometimes, of course, you want to have in the model, in the end, a model which is good at several tasks. But maybe can we create some type of task that is good to learn general knowledge, which we can then easily transfer? That is somehow the main idea. So again, traditionally, we have seen the main way of doing it is to do this type of data collection, then create your architecture, and then perform your training. And we've last time seen that the main challenge here is that typically really we have not that much data. It's a long way to collect this data, because often you have very specific things you want to have. And there is not just the naturally this data can be get from someone. That's why we looked into this transfer learning setup, where we train our initial model on some task, which hopefully a lot of initial data, and then we have this type of good starting point, since the hidden representations are somehow helpful, and we can use some initial training. And we had a first step into looking what is a good way of training your initial model. So there was already this idea of maybe it's not important to train a model really which is good at a specific task, but the idea in meta learning was now that we are training here a model which is not really good at one task, but where I can very fast adapt it to another task. The other way of thinking of it, that is thinking about the learning. The other thing which is important is here, of course, the data. So which tasks are where we have a lot of data? And then the question comes, oh, maybe we can think of other tasks which are not really interested at all. And all the tasks we'll today look at is really the task itself is not really an interesting task. Normally, the interesting task is that you get then a very good initial model, and then you can fastly learn your task. So the question is, can we get somehow, tasks which are good to learn this type of initial model? So, and there again, this which means what is a good, I mean, the first question there is, what is a good initial model? A good initial model should somehow learn the hidden structure in your data so that it's easy to extract things and learn the right things. So, I mean, for example, if you have words, it might be important that the model somehow has learned what are the different functions of the word, because you will need that for a lot of tasks. In order to understand a sentence, you need to know what these things are. So the idea is, can it like somehow extract the important information and have them more obvious so that it's easier to somehow do the task? And so the question is, on what type of task can you do that? And the idea in self-supervised learning is, now we don't use any task really where we have collected data, but we look at our task, our data we have, and now we look at unsupervised data. So where you didn't have to go and annotate it by hand, but just data which is out there. So text or images or anything like that. And we've used them in unsupervised learning, but from an architectural point of view, you can do clustering and so on, but that's quite different types of models. Here, the idea is, can we make an artificial task where we have the solution already in the data, and we're just showing not everything to the input, but only part of it, and then we let the model learn these tasks. So it's somehow the inverse way. Normally, if we have annotated data, we take our data, we add some information, we put there the class that this is a cat or a dog or anything, or in text, we generate a translation, so we can generate a translation model. Now we're doing the inverse step, which is easier. We take our data and we remove some information or do something with it, and then we have created like the data and try to predict it. And there's different ways. So the one thing approach is more on a compression-based method. So the idea is we try to compress our data. The idea is, if we have to compress the data, we need some of the most information data to be represented. The other question is to do predictions. So you remove some information from your data, and then you're trying to predict this information. And this is, of course, you can automate it. You take data, you remove something, and then you try to predict them. So we'll see, for example, for image, one idea is you remove the color information. So you only have then a black and white image, and then you're trying to recolor it again. So you try to learn a model which can do the coloring. And you as a human can do some type of coloring, but there you need typically you try quite some understanding in order to know whether that a banana is always yellow or mostly. So you have to know that this is a banana. And for text, you can do similar things. We'll see the typical thing is like a prediction of some type of the text. If I give you a sentence and only give you the start or remove some words in between, maybe you cannot directly get the correct answer, but you have a good estimate of what is possible. If I say I live in, then you don't know. I mean, with all your knowledge, you will most probably estimate that the chance is very high that it's Karlsruhe. But at least in general, you'll know now should be a city or some other object, but it can't be a word. So you have to have a lot of knowledge in there to do that. So the nice thing is, in all these cases where we predict missing things, properties, or so on, we build a model. The task is quite challenging because you really need to have a lot of knowledge to do a good estimate. Often you can't do the perfect estimate, but that's also fine. But it's easy to do that, and you can just train it on all the data which is out there. And that's exactly what is done in large language models and so on. You don't have to really like correctly collected, you just take all the data that is there and try to predict some stuff. So the main focus of today is then on the first part. So if we're talking about self-supervised learning, that's typically applied in a like some type of transfer-based approach, where we initially do our self-supervised learning on the initial model, and then we have some type of supervised data to do then the second step. And today we'll only look into what are good tasks and good ways to train this initial model, so that we can then do the transfer step and easily learn then the second part. So the idea is, again, the target of the self-supervised learning is not to really solve an interesting task, but to learn good type of hidden representations. So that can be here for sentences that you have like meaningful, in some way, hidden representations that represent each word in the context, for example, telling us what is somehow the meaning. Or for images, you have a good representation. And then in the second step, you can do your supervised learning. You only have to do the learning here. For example, classifying this as whether this is a fact, a question, or anything, or whether this is which type of object this is. And the idea is that it's typically easier to do just on the single hidden representations or a sequence of hidden representations than to do that on all the things that we're having here. Yes, so this is somehow the main motivation. And then comes, of course, with a challenge. And the main challenge is, how do we learn these types of very good representations? So you want to encode there somehow that these informations are important to serve the task. And this is not as easy, because you always have to remember that, neural networks try then to find an easy solution. And that is often making things difficult, that you prevent this type of loopholes. So if there is an easy way that the information is not really good represented, then the whole usefulness of that is important. So it's really the question is, how can we make these type of artificial tasks that we can easily learn or that we have encoded the most important information and can extract them easily. One group of ideas is to do compression. That the idea is, if we compress all the information that are in the input into something, then hopefully this representation is more meaningful and we can more easily extract information. I mean, it's also, of course, in general, if you have a smaller vector, you need less parameters then to extract. Of course, the important thing is that we learn some of a representation where still all important information are in there. If the informations are no longer in there, then we can't solve the task and do that. And the typical way of doing that is to do that with an autoencoder. So let's have a look at the most simple or easiest autoencoder. An autoencoder, there again, the idea is, okay, we're training now a network and we don't have labeled data. So what do we predict? And the idea is, let's autoencoder reconstruct the input. So you give an input, and then the task of the network is to reconstruct this type of network. How does that go? So we have here our input representation, our input X. Then we're having very simple neural network, just some matrix W1, which represents this into our hidden representation. Then we are taking a second parameter W2 to get our reconstructed input. So H is then calculated as W1 times X, and X dash is calculated as W2 times H, and then we have our reconstruction. And the parameters we have to learn is now W2 and W1. We have to somehow learn good parameters here. how do we train that? So what will be our loss function here? If you would have the task, how would you evaluate if the model is good or bad? Any ideas? Yes?
I need some kind of reconstruction error for an image, like pixel distance for each pixel.
Yes, pixel distance. So again, just in general distance, exactly. And it doesn't even need to be an image. You can, like, at least in general, of course, you can then encode there a lot of domain knowledge. So how are two inputs more similar or less similar and so on. The easiest thing is you can just take the two. I mean, to your network at some point, these two have to be vectors. So you can just do the difference in the vectors, calculate that, and that is your loss. The nice thing that is differentiable, so you can then use that, backpropagate and learn a good point. So this is yeah, quite easy to learn. If we're just doing that this way out of the box, well, we always learn a good representation here, which is really helpful in our encoding. Or do you see any loopholes that the model will not really learn a good representation? Any ideas? Maybe I motivated it already in a way that these loopholes don't exist, but generally, if you look at this type of matrix, what would be a very easy solution where you have a reconstruction error which is even 0? Yes? Yes, exactly. So if our hidden size is as good as as big as the input and the output, we can very easily get a perfect solution by having W1 and W2 as identity matrices. In this time, X and H and X dash are all the same, and we have a loss of 0, so we won't learn anything. That is the best we can get. But this model doesn't help us anything. I mean, you have just copied your input. So for any further neural network, if you do transfer learning, it doesn't matter if you start with this representation or this representation, they should be both as good because they're exactly the same. So just auto-encoding the stuff doesn't really help. So we somehow have to prevent the model from doing that, but to learn somehow decent, good representation. And this can be achieved in different ways. So the first and easy one is the one I already mentioned at the beginning, which is compression. So if we're now saying that our hidden size here is small compared to the input, then of course we can't learn that because we somehow have to encode efficiently what is in the middle there and then reconstruct it again. Yes?
Because the reconstructed input has the dimension of H.
Yes, that is a good point and wrong. This, of course, has to have the dimension of D. Thanks. Yes, I copied. You see, the PowerPoint formulation takes too long. So yeah, thanks for pointing out. I corrected. So this is, of course, the size, the dimension of D. Otherwise, we can't easily calculate this type of loss. I mean, we also want to reconstruct, so they should be the same. So yeah, so they have to have these have to have the same size, but here we make a small hidden size, and then we can't just put everything in there. So we need to learn like a compressed version, which hopefully has then the most important information. Another thing is we can add another loss. We can say, oh, it can be as big, or in sparse autoencoders, it's even often bigger, but we say the representation should be sparse. So most values should be 0. So you can, for example, calculate here the length of the vector, and that should be as small as possible. So you can try to achieve a representation which is somehow the contrast to what we had before, this should be very dense, very compact. Sparse autoencoders do the different thing. They try to have only very few values non-zero, and then you try to encode there the most important. There's a third option. Any idea what else we could do to make this task more challenging, so that just copying the input is not really helpful? Then going already. Oh, yeah.
Removing something?
Yes. So that's not really then the prediction, but that's what people call denoising autoencoder. So the idea is we put some noise to that and removing information, or just in images blacking them out, or I mean that's easy, or like in text you can just also replace some words or something like that. So then you make this input no longer really perfect, and then it has to learn, of course, a lot more in order to reconstruct it. If you think about it, if you have like some black pixels in an image, in order to learn what is a good value for these pixels, you have to understand a bit the images to have a good estimate. Or if you think about words, if there's like one word missing, you can often estimate a good probability of what is a good word, but you have to really understand the sentence, know a lot about it in order to do this type of thing. So these are all ways where you try to reconstruct your input again, and yeah, have a representation in between, which is good. The other task, which is currently, yeah, maybe even more commonly used, especially for text, is the prediction tasks. So we try to predict something as the input. It's again, of course, then in some way we'll see related to this idea of autoencoders, where you also predict. I mean, you could also say here you're predicting, at least in the second part, it's no longer compression, but here it's already some type of prediction. One way of doing that is the language modeling. So in text, it might be either that you predict the future, so you give it a prefix, a beginning, and then you say, what is the best way of finishing this sentence? So how should we finish this sentence in order to get to a representation which is really, and to get into the sentence which is useful? And again, you have to understand the text, or you remove something in the middle. For images, things are a bit different, because there's one big difference, that words are typically discrete. You have like a fixed number of words that you can predict. Images and audio, at least naturally, are continuous. Of course, on a PC at end, everything is discrete. Things are a bit different there. So you can do this type of color prediction, or you can try to add things like how to fill in the gap here in the image. The nice thing about for the language model, it also really has some long-standing history in the domain, so in natural language processing. So there is this type of distributional hypothesis, which was like 70 years ago already said, which says you should know a word by the company it keeps. That means if you're seeing in which context, so in which other words a word is occurring, you can good estimate the meaning of a word. For all of you, you will all the time hear new things, new words you have never heard before, but by seeing the context where the word happens, you often can estimate already what is meant by it. So if you're hearing something about a new restaurant, somebody's just mentioning a restaurant to you. You've never heard the restaurant name before, but since he's saying, "Oh, should we go this evening to have dinner at XYZ?" then you already know that XYZ is a restaurant, because where should you else go to have dinner? And then this means, yeah, there is really this is a very interesting task. You need a lot of if you can solve the task, you have really a good understanding of the text, and therefore it's perfectly done for learning and understanding. And the good thing is we can do that on really large amounts of data. So we can just train on every text data. You don't have to do any manual annotation on that. The only thing you have to do is download the data. And that is, relatively easy. And that's why we can now train on billions of documents, because, if you would have just manually, even like any person has to go through it, or that's not possible. So you can only do that because you can do this automatic tasks. Besides what we talked before, the predicting something which is missing, there's also other things that you can do. You can predict properties. So that is, for example, is it that if you have the two sentences, I live in Karlsruhe, it's a nice city, can the second one be the sentence after the first one? In this case, it's possible. But if you have the two sentences, I live in Karlsruhe, today I go, I watch TV, that's very unrelated, and typically you wouldn't have seen them next to each other. So again, it's a very easy task. You just give it two sentences and you predict whether you found them one after each other or you randomly selected them. And again, you need a decent amount of knowledge to do that. Another example from image is this spatial arrangement. So you take one patch of an image, like here in the middle, and what you then do is you give it one other patch, like this one, and it has to predict how is the arrangement. So that, for example, you see the blue one, you have 8 possibilities, 1, 2, 3, 4, 5, 6, 7, 8. 7 is below, 2 is above, and so on. And then the model has to learn that if you have this image and then see this, then the relation is the relation 3. So you have here a classification task with 8 possible outputs, and the model just has to learn. And you can, like from any image, you can extract this type of patch and then give it the test. You see, in this time, human maybe should be possible to do that. Of course, it might be difficult. That's not always the case. But again, there the advantage is if you have large amounts of data, if there are some things which are not possible, very ambiguous, that's typically possible, and you can do that. There's also the relation. So for one nice, especially for image, what people, that's of course again related to the properties. But what you can also do, is we'll see that, is that you take the same image and then you can apply standard operations like image operations. And then you can like drop it and resize it. So take a part of the image, you can flip it, you can remove the color or change it, you can rotate it, you can add noise to it and blur and so on. And then you give an image you can give a model 2 of these images and say, now, is it from the same image? So is it the same image, or is it from some other type of images? The other task would be you give it a dog and another dog, or a cat, and then it says, no, these are 2 different images, while these are from the same image. And again, you have to learn a decent amount of understanding of the image in order to do this type of task, whether these 2 are related or not. Before we going into the architectures and then later going into some examples in depth, it's a general idea of how to create self-supervised learning tasks. Any questions to that? Good. So there's we'll see there's typically, different type of architectures. And I just wanted to give a high level overview of what they are typically are. So if we're doing prediction tasks, these type of architectures typically look like that. We have the input, and then there is a neural network, which we'll refer to as the encoder. which learn some type of a prediction, a representation, and based on that representation, we can then do the prediction and, for example, compare it to the label. Sometimes we're not taking the highest representation, but what we're having, for example, is we have in between a representation, then we have a decoder, and based on that, we do a prediction. But later, we are not interested in this top, so that's a big difference. We're not interested in the hidden representation here, but this is the final representation we are interested in. So we're trying, maybe like we can remove some information for our task, but for the representation we are later working on, we want to keep this type of information in there. And finally, there is the idea of comparison. We had that in the relation. It might be that we have this type of architecture where we have the input, and typically both inputs are encoded with the same encoder. So we learn a hidden representation for both of them. Then we might do some more thing on that, and then we have a comparison as a task. So in this scenario, it's not about predicting something, but for example, saying whether two inputs are the same or not. And then we'll have this, what is also referred to as Siamese networks, where we have the same network in parallel applied to two inputs, and we later do a comparison on top of them and try to learn that things which we want to have so similar are the same, are as similar as possible, and things which should be very different are different here too. And we'll see that at least most of the type of use cases we look into, we can have some type of this more general architecture. That, yeah, type of general architecture might now sound very abstract, and that is fine. And therefore, yeah, the rest of this lecture, we'll look at very different use cases on where you do that. We'll do that at 3 modalities. So we'll look in language, how this is done. Then we'll look into how this can be done with audio input. And finally, for images, how that also can be done. And we'll see, especially in audio and visual, we have the additional challenge that we don't have this type of discrete output, but more a continuous one, which we have to address. In the case of language, one big difference we will see is we naturally will come to different types of architectures that you can train with them. And these architectures we partly have learned already. If you remember, we had the encoder-decoder setup. There's a decoder-only model and encoder-only models. And we'll see that, yeah, depending on what type of architecture you want to have in the end, so what type of model you'll need, you will have you'll have to do a bit of different pre-training, or at least the pre-training is typically better. It's not that if you have a single task at the end, if you want to solve a task, you often can use different type of these architectures, but yeah, just the pre-training you have to do is differently. And we'll see, for example, the decoder only, which seems maybe we'll see a bit of the most limited model we have. The big advantage is that we there can do a very efficient type of pre-training. And therefore, interestingly, recently, people more switched again to going to decoder-only models. That's why we refer to as large language models by now, because really the main advantage of them is that we can so efficiently pre-train them, which means we can just use more data, and they're therefore at the end the most strongest one. If we think about pre-training or self-supervised training on language data, this is typically done by the language modeling test. So let's go a bit back. What is a language modeling task? We'll do their short view on that, and then see how this is naturally very helpful for the for pre-training large models for text. The concept of language modeling is really, really old. So it has been done, I think, for the last 40 years at least or so. And originally, the idea was we want to automatically learn, and that is again what is matching to what we want to learn, automatically learn the sentence structure. So without manually annotation. And the traditional language model tries to do that by estimating for a sentence how probable is that this sentence was produced by a native speaker. So it should give us somehow this is a good type of sentence. And of course, there is a lot of information in there that maybe makes them so possible. So in language in general, you have the one hand syntax, which is about how to structure a sentence. There is otherwise the semantics, which tells you what is the meaning of the sentence. And a correct sentence should be both semantically correct and syntactically correct. But of course, you can have sentences which are syntactically correct, but don't really mean anything. Color eats bananas doesn't make any sense, but it's a complete correct sentence in English. You can also have sentences where you can understand the semantics, but the structure is not really correct. If in English you miss the third person verb, like S on the verb, he walk fast, you would get the semantics, but it's syntactically a wrong sentence. So what a language model should do is give you something, the house is small, that should give you a high probability, that is a sentence that you can say. And if you have small the house is, that is not really a good sentence. So that should have a very, very low probability. So how can you build this type of model which tries to predict you, okay, this is a very good sentence, or this is a quite bad sentence? The first idea is in traditional learning, you just estimate it. You count, like how often does a sentence occur, how many sentences we have. So if you want to know how is good morning a good sentence, you count how often you see in your corpus good morning, you divide it by how many sentences you have, and then you have a good estimate. The problem is this is somehow a bad model because you can only do that for all the examples you have seen, and you can't do that for any traditional model. So therefore, you somehow have to do a different type of modeling. If you would again view that as neural network, you just encode this all sentences, you number them and try to predict the probability. Most of the time you'll see a sentence that you've never seen before, so you can't input it anyway into your neural network. So you have this sparsity problem. So we have to somehow split things out. And the nice thing is in language, that's quite easy. And we can split things up into words. So splitting like a full sentence into words is quite natural. And there we can use a chain rule that tells us how probable a sequence of two words are, A and B. So the probability that you first write A and then you write B is the probability that you first write A times the probability that you write B, given that previously you have written A. This is just a reformulation of what we have done as the conditional probability here. So that's the definition of the conditional probability. The probability of B given A is the probability of A and B divided by the probability of A. The nice thing is, I hope all you know this the first time still from your statistics and probability theory. The nice thing is that you can easily extend it to any number of variables. And that is important, for example, for language, because that means we can now calculate the probability of a sequence of words x1 to xn as the probability of the first word times the probability of the second word given the first word times the probability of the third word given all the previous, and so on. So this way we can now do the language modeling probability by breaking it up into individual decisions. So the whole decision of what is a good sentence, you break now up into the steps of creating the sentence, of first creating the first word, then creating the second word, and so on. And quite naturally here, of course, whether the fifth word is a good word or a bad word depends on all the words you had before. So if you had before some words, then the probability will change. If I start the sentence with I, then the next word should be a verb. While I start with my, then the next word will be most probable an adjective or a noun. My house I can say, but not my walk. I mean, okay, my walk, if walk is then a noun, but my eating doesn't really work. And then you can easily now do that as an example. So you can estimate the probabilities of the full sequence. Its water is so transparent as the probability of the first word given the probability of the second word given the previous, and so on. So here now you have split the full sentence probability into individual ones, which is a first good step. However, we haven't solved our problem really, because in order to estimate this probability here, we would still have to see all the words. So we still have somehow this type of problem that in order to calculate our conditional probabilities, we would have seen all histories. And the longer our history here gets, the more problematic it is. And that's why we have to do some type of clustering. So we can't calculate this probability perfectly, but we have to somehow estimate it in some way. And we'll see, we'll have a one slide look in a traditional approach, and then we'll see how we can do that now in the neural stuff to train our models. And then we're also seeing again how we are using that as pre-training. So we somehow have to replace the history here by a class. And that is, of course, not correct anymore, but it's, again, a good approximation. For a long time, there was a very simple solution to do that, which is somehow a strong baseline. Does anybody know how to do that without neural networks? You heard it from somewhere else. So the very easy thing is you can do what is referred to as a Markov assumption, and which leads to n-gram language models. So you're saying which is really far apart, doesn't really matter anymore. The most important in language is also what just happens before. That is the most important. So you're just saying, oh, we approximate the probability of the word the given all the history by just the probability of what the word the given the history, the previous word. So somehow, or you take the last two words. I mean, that now depends on your hyperparameter, but your clustering is that the whole history gets represented only by the last one or last two words. And that is what is traditionally the n-gram language model. And then you don't need any neural networks. That's how you can still estimate the sequence of words, and it somehow works. So this is a general concept, this type of language modeling, which has been successfully used again to train and to say, like, to model how a language is fluent. Often you need it. If you think about automatic speech recognition, you would see you can just take the audio and guess it. But often you can't hear everything. And therefore, you really need the context, which you get with a language model, which tells you, oh, at the next word, some words are more probable and others are less. So even if you don't understand it correctly, you can often guess what is the next one here, or do like a good approximation and then only distinguish between these ones. So this has been done very long. And again, here neural networks are somehow a very good and helpful application of doing that. We can easily create a neural network which exactly does the same thing. It's like predicting the next token based on the previous. So what we did here, we model the probability of the next word given the previous one. We can do that very nice with, for example, in RNN, where we then always predict the next word in here. Yes?
Do you think that text recognition already works like that? That it also regards if it's really probable that the word computer stands next to horse or something?
What type of text recognition do you mean?
Like if you recognize handwritten text.
Yeah. They always use language models also in that. Yeah. So both in automatic speech recognition, in handwritten recognition, in machine translation, in all these things, they somehow have these language model concept in there. I mean, nowadays they're all neural, so you partly have these information no longer separated for a human separately, but you have it integrated in one large neural network. But you I think nearly always you will have this type of information in there. So how does it work? So you see already a bit your recurrent neural network, which is there to do a language modeling task. So we have to somehow invent one new special character which says, okay, now start generating tokens. Because, I mean, you have to have this start probability. Here we did a bit of a trick. You see, you have conditional probabilities only for the first part where we only had P from A. Of course, in neural networks, it should always be the same. So the trick is we are saying, oh, this is not P from A, but this is P from start of the sentence. So given that we're at the start of the sentence, what is the probability of A? So you can do that then in the neural network. So what you're saying is, yeah, okay, we start with a sentence. And then the first correct prediction in our example would be I. Then we're giving the model, now we have sentence start in I, and then predict the next word, which would be lie. Then we give in live, we give in live, and then it's in, and then in and Karlsruhe. So this is really now, if you train this type of model, it will hear how is your output you modeled, what is your top layer in order to do some model like this. This will be a classification layer where you have the whole vocabulary in here. And then here you have the output probability that how probable each of the words is, and you train it that I should be the correct one. And so you go on to generate all the words. So let's do the architecture step by step. So this type of neural network, this language model, looks typically like that. So we start with our words. Then the next step is, we said already words are like other categorical values are typically encoded in this one hot encoding. So you have then this one hot vector, which says you the word I is maybe word number 527. And then you have a vector of your vocabulary size, so all the words that you know. And then at position 527, you have a 1, and all the other vectors are 0. That is somehow your initial one hot encoding. Based on that, then you learn one linear layer, which maps them to word embeddings, so more dense representation. The problem is your one hot encoder is typically has like some dimension of maybe 10,000 or so. That's normally not a good hidden size to work with. So the first thing is to make things more dense and learn their good representation. Then you have this smaller word embedding size of, let's say, 200 or 1000. And then, for example, you can have here any type of sequence layer. So the RNN layer, and then on top of the RNN layer, you again have a classification layer where your targets are again one hot represented. So you have a layer then which goes, a linear layer, which goes from your hidden size of the RNN, let's say 200, to the output vocabulary size 10,000. On top of that, you still have to do one more step in your classification layer. What is the activation function you will use there? Yes? Yes, exactly. So you want to have a probability distribution over all your words, and then you get that by the softback, so that the sum is 1 and all values are between 0 and 1. So you can then interpret here your output as a probability distribution also. So what does the model then do? So you have the RNN. So the prediction here depends on what you've seen here and here. The prediction here depends on this hidden state. This hidden state depends on the last word lived and the previous hidden state. This one depends on I and the previous hidden state. And this again depends on this one. So you're really predicting the probability of this word depending on all the words that I had before. So you have learned then this type of probability of the word in given all the previous words. So with an R and N, you can very easily model this type of language model probabilities. And if you want to have the probability of the full sentence, how would you get that? So we're saying at this position, we are getting the probability from the neural network of in given I live. How do you get now the probability of I live in Karlsruhe? Yes?
Multiply each probability.
Yeah. Yes, exactly. So you take this probability times this probability times this probability times this probability to get the overall complete probabilities. And of course, you don't need to take only an R and N that you have hopefully seen. You can, of course, also use there some type of self-attention that you always attend to all the previous one. Again, then this probability depends on all the previous ones, and you're getting the correct probability out there. That is the type of architecture we're using. Now, how do we train these types of models? Our input is a full sequence with, as a start, you have the sentence start token, and the output is then without this token at the beginning and predict. So you see that again, the nice thing here is that we are able to not use any additional data. So just based on the sentence, we can use the sentence as input and as output, while just always predicting some of the next token. So you always predict here the next token. You don't have access to the word in, so you can't just directly look at it because you're only predicting on the prefix. So you're training the model to always say what is the most probable next token. And you can do that in parallel. So you're getting here your full sentence as input and predicting your full output sentence. And then since it's a multi-class classification problem, or you typically do like cross entropy. So that's the probability, the way you train. So more in detail how these steps work. So you do, if you give an input sentence here, like this is an englischer Satz, you calculate your forward pass, and at the end of your forward pass, you have the probability distribution here. So you have, we said the top layer is really the number of output vocabularies. So you have here the probabilities for like, what these are the probabilities, what is the first word? These are the probability, what is the second word, given that the first word is these. These are the probabilities, what is the third word, given that the first words are these, is, and so on. Then you have to measure your error. Your error is you look at the position where your correct words is. So here, for example, the probability of these could be 0.33. This is the probability of ist, and so on. And then the error is just like the logarithm of this output. So that you sum up and calculate that as your error. And then you can do this type of backpropagation to backpropagate these errors and change all your weights in your mean. And this is really now one big advantage of the neural language model-based approach compared to what we'll see later. If you think about efficiency, so how fast do you learn? If you think of this as one example, so you give in one sentence here as input, And you're not only learning to predict one thing. At each position, you get a feedback signal, like which was a word there. So you're really getting, like, for each word, you get also one feedback signal, which makes the learning very efficient, because with one example sentence, you're learning a lot of things. You're not only like need to predict one single thing, but you really learn all of them. So if you think about your n-gram formulation, so you're not first learning how probable is that ist is coming after dies, and then you're doing a new example that you're learning what is that ein is coming after dies ist, and so on. But you're doing all these signals with one feed forward and backward pass, which of course is very efficient in order to learn these types of neural networks. Any questions to training this decoder-based models or neural language models? Good. I mean, just as an example, you can, I mean, traditionally we say we're not really interested in using them, but we'll see later, especially for language models, although they are somehow self-supervised pre-trained, they are, and these architectures are very interesting to also use them in decoding, and that's very simple. So if we now want to decode, we can, for example, generate what is the most common sentence, or if we're giving a prefix, what is the most common way of continuing. And that works somehow very similar to what we had before. So we start here with our sentence star, we put it into an RNN, and then we get here an output probability distribution. So a distribution over the whole vocabulary telling us how probable each of the words are that is the next. And then we can, for example, take one of them. I'll take the most probable one, maybe this one, and put it in there. So these. And then we again run our RNN and get a new probability distribution and check what is the most probable one. And then we get ist and so on. So this way we can use the decoder, like this type of neural network, also to generate things. Of course, if we always take the most probable one, in this way of application, we'll always get the same input output, which might be a bit boring. We get the one most probable sentence. But we'll see that there are other ways of how to efficiently do interesting tasks with this type of info. Then, one last question about the type of clustering we had before. If you remember the language modeling we had before, we said that we are somehow have to cluster all our histories into like some classes because we can't estimate the full probability. So the question is now, what are we doing now? Did we solve this problem? So now the probability of Karlsruhe depends on in, on live, and I, and on sentence start. So it seems, can we now calculate really the probability of Karlsruhe given the full history? So there's no type of clustering or approximation happening where we can calculate this correctly. Any comments on this or any ideas? So how long the history are, we will always use all the full history perfectly, and the probability depends on all the previous tokens.
Like a fixed context window for
There's not a fixed context window, but there is something fixed in here still, which not the input size. I mean, the input, you can have an RNN which is arbitrarily long. You can include all the 50,000 words before and still calculate the RNN. Might be a bit inefficient and slow, but from the model that works. Yeah? Yes, but still the hidden size of the RNN here is fixed. And all the history we get. So this here depends only on the hidden size here. So therefore, we still have somehow this type of bottleneck. The nice thing is this time we didn't, as a human, go there and say, oh, only consider the last 5 words, but we somehow in the RNN learned what are the most important information to store here to do the task. So we are not doing like any human-based, like fixed type of context, but we're trying to learn in our hidden representation what needs to be all stored there in order to do that. So therefore, we have still some type of clustering. And if we have a limited hidden size, we cannot store all possible histories in there. But the nice thing is we are learning the hidden representation. And therefore, we can also, and that is important, we learn this hidden representation. So we can also learn which representations should be similar so that these are packed together and the predictions will be similar, while what other types of representations can be different, and thereby we should have them separately. And also, of course, if we're using self-attention, it's not that we then have solved that. I mean, then we can access everything. But in the end, if we're doing the self-attention, we are using this as query to compare to all these keys, and then we are calculating our value, and then we are doing the weighted sum of the value to get the context vector, and that is the only vector which is put in here. So again, you have some type of bottleneck that only these informations which fit into the context vector are passed to the next level. Of course, now before in an RNN, the hidden state only depends on the previous state. The context vector can depend on all of them. So you can have more different type of information flowing them, but still you have some type of limitation that only what is in the context vector can be passed there to the next text. So yeah, this type of neural language model is like somehow we do it a prediction task. So we do self-supervised learning with a good type of based on the full prefix as we have here. And that means what is really interesting is we are learning here a good representation for the prefix or for this word in the left context. So since this language modeling task is an important task, if we're now looking at more from a self-supervised learning perspective of what the neural language model really learns is we are interested in this hidden representation, which compacts the whole history to do this type of prediction. So we are this type of representation is then helpful to use it for maybe other time, because it really has summarized everything what was before there in an efficient way in order to solve these tasks of predicting the next word in there. So from an architectural point of view, we have the prefix encoded in there. Then we have a representation of the prefix in here at this position. And based on that, we do the prediction of the next word. And maybe an additional advantage is that we don't have to, like, for each prefix separately now train the model. But if we get in one sentence, we are training this type of thing for all prefixes jointly, like in one forward and backward pass. And therefore it's efficient. So this is somehow the big advantage. There's also like maybe one disadvantage of this type of architecture. I have a bit pointed out here again, what is like some of the limitation in here. Any idea? Yeah. Yes. So you don't have information from the future. So you don't have the right context. You only have the left context. And of course, I mean, most informations are in text are always at the left because we somehow read also from left to right. But the task sometimes would be easier if we have knowledge about everything. And that's why there's a different type of architecture, where we try to learn here a representation which depends on the past and the future. So it should somehow represent the full context, but not only of the word in, not only looking at the past, but also on the future. And we know this type of model, so we can do a bidirectional RNN or a self-attention that will look at everything like that. So I guess all of you could build this type of model, I would hope, to do that. So you again have a one-hot encoding, word embedding, then you could here have a bidirectional RNN or self-attention layer or several of them, and then you would do your word prediction. However, there's one challenge now. Well, if you train the model like that, will it learn a good representation? Yes? Yeah, but the whole sentence is available if you train it. If you train it on a sentence, you can give in here your full sentence. So you give in here your full sentence, and then you predict it to here predict Karlsruhe. Yes?
Yeah, for the bidirectional model, you already know the next word, so you have to mask the word to learn something.
Yeah, so if we would just do that, it would not learn a good representation, because the only thing the model would learn is, in this case, to always look at the next word, get the information here and put that. So it wouldn't try to understand the context or anything. It would just learn that in this RNN layer, it always has to copy the input to the hidden state so that we can give that further to the next thing. So it wouldn't be really a helpful, good task. That is what I meant at the beginning. You have to be careful that you develop a model where there are not these loopholes so that the model doesn't learn anything, but where it really has to understand where the task is challenging enough so that the model really learns something. So we have to do anything, something that we can still do that, because now the future context is known. So predicting the future is no longer really a helpful task, because if you predict the future but know the future, it's a bit boring and not really needs a lot of understanding. And you already mentioned how to do that. So the thing you have to do is that you have to somehow mask things. So if you have a bidirectional model, the idea is now that you mask the model here and then do this type of prediction here. So there, the big advantage is now that you can use it to do this type of prediction. There's two disadvantages also that you should keep in mind. Do you see any disadvantages? So the one thing is where we talked about efficiency. So we said in a language model, if we put in a sentence, we get feedback for each word. We always get feedback. Here in this case, of course, it makes only sense to predict the words that you have masked. So it makes sense to predict the third word. It doesn't make sense to predict here the second word, because that you have in there. And on the other hand, of course, it doesn't make sense to mask all words, because then you still don't learn any. Should you guess a sentence without knowing anything? So what you have to do is you have to mask some words here and then predict them. But that means you're no longer getting feedback for each position, but you're only getting feedback for them. The other thing is in the application. Now you can only do applications where you have access to the full sentence. So in training data, we have that. But I just showed you before, in a decoder model, in a unidirection, you can generate a sentence or something like that. Here, of course, it's now difficult to generate a sentence. You can do some filling that you mask a word and say, what is the most probable word in there? But you cannot really generate anything, because you need to know the future, because the model is trained to know the future. So it will not work good if it doesn't know the future. Yes?
What can you use it for then?
It was used, this is like BERT. So you can do classification tasks. If you want to know what a named entity is, if you want to classify the sentence, of course it is advantaged because it has all the types of information in there. Yeah, one successful model of doing that is what is referred to as BERT, which is called, which is doing this type of bidirectional model using masking. It is doing it with a self-attention model. It was like one of the first like encoder. Now we're at an encoder model where the task is not to generate something, but just to encode all the information. The interesting thing, it does not only do this masking, we can combine it then with other types of losses. For example, typically people also trained it with the next sentence prediction, where you put in 2 sentences and then you do the classification task we had before, saying, are these 2 sentences that follow each other, or are there 2 random sentences we just put in here? Let me just finish shortly the basic idea of BERT. So you mask words with different probabilities, and you have this next sentence prediction. So at this one, the man went to the store, he bought a gallon of milk. You have masked some words to also predict that. In this case, it is the next sentence, while the man to the store, penguin are flyless birds. These 2 sentences don't make sense together, and they're not next sentence. So yeah, we'll finish with these encoder models next time, and then look at other models, and finish on Thursday the idea of self-supervised learning. Any final questions? Good, then see you back on Thursday.